I think Dushyant must have given an introduction about our initiative and the what the essence of this journal club meetings. Our plan is to have once a week or twice a week, maybe once in 2 weeks, similar meetings like this, where we would some of us would read one paper or two papers on a particular topic and try to present the essence of that paper, what the researchers tried to do, what they did, so that at least we get a good idea of how literature review, literature study is being done, and how we present papers in conferences, and how research presentation, and how papers are written. It will help all of us grow together. So, since this is the first meeting of this kind, what I thought was to I'm from engineering background, and I'm mechanical engineering passed out from Jadavpur University. What I thought was, since almost most of us also from engineering backgrounds, and we want to transition into physics, I try to present. I will be presenting some papers which are from engineering background only, but they study the core physics of the topic. At the end, engineering is all about application of physics, so there will be physics also and application also. But these papers will contain more of physics and less of applications. So since we are new to this, so it would be good to start. And since this is first meeting of this kind, and almost all of us are new in literature review of papers, so I when we'll go and study papers, research papers, we'll see that there is a difference in the content of papers and the content of the textbooks we read, the textbook physics. So there is a transition. We need to learn what is the difference and how to extract the required information from the papers. So what I tried to in this presentation, I tried to keep it a mixture. There would be some content which would reflect textbook style knowledge, and some content which would be representing the type of knowledge and type of content which is there in the research papers itself. So since it's the first meeting of this kind, so I thought to keep it simple. So textbook style content it would also be there. So moving on, I will start with the topic. The topic is turbulent flow through sudden expansion. We'll see one by one what is turbulent flow, why sudden expansion geometry is important, what is sudden expansion geometry in itself. Here we see what is a sudden expansion. By sudden expansion, we mean that there is a duct flow or a pipe flow, fluid flowing in a duct or a pipe, and that duct or pipe suddenly changes its size. By size, I mean its characteristic length, which is for pipe flow, it can be the uh, the diameter of the pipe. And because of this sudden change in geometry, there are certain flow features. For certain flow features would be developing in the flow, which are very, as we go along, we'll see that these are very interesting flow features. And in case of turbulent flows, there are many more interesting phenomena coming up that would be seeing, and what are their consequences both for engineering purposes and for the core physics of the flow problem. Yeah, as we can see there, we have shown a duct flow, then I've shown a schematic diagram and a pipe flow with sudden expansion geometry. This pipe flow, especially I conducted experiments in this pipe flow setup at Jadavpur University, Kolkata, in the mechanical engineering department. So here we can see there is a pipe of smaller diameter, then suddenly the diameter has increased to a larger value. So there is a sudden expansion. So this is what we mean by the term sudden expansion of geometry. And there will be some very important changes in the flow pattern, flow geometry at the point of expansion. And then as we go along, these changes slowly die out. We'll see as we go along. Why do we need to study sudden expansion? See, this is a type of content which you will see in the textbook. Why, what, how. Research papers won't give you such content. They will directly come to what they have done, what experiments or what computational methods they have used, and what results they have got. They don't explain much about what, why, how, why important, nothing at all. But since it is first, as I already told, I would be covering some basics as well. Sudden expansion has a lot of practical applications, which is definitely from the engineering point of view. These type of geometries are found in heat exchangers, dump combustors, pipelines, flow over airfoils, and many more applications. And from the fundamental fluid mechanics point of view, from the physics of the flow, it is very important that we study these phenomena because they give you a lot of idea about turbulent flow properties. And these flows, as we go along, we'll see what is the main motive of studying these flows. they are a very good model for the study of flows with regions of separation and reattachment. What is flow separation? What is reattachment? We'll move along and see. I read a few papers on this topic, which explains all of these phenomena, why we study this, what we have got from studying this. So in these slides, I mentioned around 10 to 15 papers which have given good results about this topic. So there are many studies conducted. People conducted a lot of studies using experimental techniques, using computational techniques, and some very few using analytical techniques. As we all know, turbulent flow is also governed by the Navier-Stokes equation, which is unsolvable, which cannot be solved in its full form. So we just take some approximations of the Navier-Stokes equations, and then we get some analytical solutions. Like for the Cout flow, we have a solution. For plain Poisson flow, we have a solution, but not for all domains. So for turbulent flows, Navier-Stokes also predicts the nature of turbulent flows, but complete analytical solution is not possible. So most of the research focuses on either experimental methods, and the more recent papers focus on the computational methods, because the computational methods are slowly developing as we progress towards the 20th century and the 21st century. So we'll see in turbulent flows, basically we have three classes of simulations: DNS, direct numerical simulation; LES, large eddy simulations; and the RANS method, Reynolds average Navier-Stokes simulation. So generally DNS simulations are very costly. They are direct DNS. By DNS we mean solution of the entire Navier-Stokes equation in its full form by computational means, obviously. So it is very costly because for turbulent flow the data generated is very large, and we would need a lot of memory as well as a lot of computational power. So generally DNS is conducted for simpler problems, and this is actually a simpler problem because the geometry is simpler, but it has considerable very good implications. And then we consider RANS equation and LES. These are a bit complicated. RANS is still simpler. We do some mean decomposition, Reynolds decomposition of the Navier-Stokes equation, and arrive at a mean equation for the mean flow and the fluctuating flow. Basically, turbulence, by turbulence we mean fluctuations in the flow. In just, if we in very vague terms, that the flow is turbulent, we mean it is fluctuating. We cannot predict; it's unpredictable. So in the RANS method, what do? We, using statistical means, we separate out, find out a mean flow and then a fluctuating flow. So the total flow is a sum of the mean flow and the fluctuating flow, and then we take a average of the Navier-Stokes equation and we separate out the mean flow and get an equation for the fluctuating flow, and then there are a lot of more equations and calculations, and we arrive at simpler equations, simpler than the entire Navier-Stokes, and then we solve for the mean flow, and then we do some simulations. So leaving the details, just for a short literature review, people have conducted DNS studies, we have done RANS studies, LES studies, then experimental methods. All are given in this this literature survey, this short survey. The author, who are what work they done, everything is given. So I won't go into the details of every paper. So as we move along the slides, we'll see what people have done, what is the summary of what they have done. So these are more papers. They are arranged chronologically. So if anybody is interested in seeing through the work done, you can just ask for the slides. After reading these papers, and means each and every paper won't contain a good description of the flow and all such things. They will just focus on what they have done, what is their work, and what they have found out, and how they have done that. So it won't be textbook style knowledge. Whatever I am talking about is totally textbook style content, and I will try to give some content of a few papers, how papers are written. So after reading all this, some literature review, after doing these 10, 13 papers or 15 papers, what I found about the flow feature, the flow of this sudden expansion, that in this sudden expansion flow, you will find that there is a potential core. Potential core, by potential core I mean that in the mid core central region of the flow, of the pipe flow, the flow is, there is a potential flow. It follows the flow is by potential flow I mean it is incompressible and non-viscous flow and irrotational flow. But as we go towards the walls, toward this I'm talking about just after the expansion, downstream of the expansion, there will be a separated free shear layer with high turbulence levels. Then there will be primary recirculation zone. There will be also be a secondary recirculation zone or a corner eddy. There will be a reattachment of the shear layer at the wall. There will be a redeveloping near wall flow. And finally, as the flow progresses, the flow will start redeveloping and it will form a redeveloping outer shear layer. Finally, it will become like a parabolic profile as we go much away from the expansion zone. Since these terms are very complicated, by reading, I'll show you the diagram. So as you can see that there is flow going, there is a duct with some height, and at some point the height suddenly increases. So at the point where the height increases, because of the large pressure gradients there, the adverse pressure gradients there, because of the change in geometry, the flow separates. By separation of the flow, I mean, suppose the flow is moving very smoothly and it is in contact with the walls. Suddenly, because of a change in geometry, the flow separates. By separation, I mean the flow is losing the contact of the wall. So the flow is separating. This is the vague meaning of the word separation. So the flow separates. So this is what I meant by a separation zone or a region, a separating shear layer. So the flow separates. Then, since the flow separates, the region where there is no flow between the wall and the main flow, the potential core, there will be a recirculation zone, that the flow is having in the recirculation zone, the flow will be moving in eddies or vortices. And then as the flow goes along, there will come a point where the flow again joins with the wall or with the domain boundaries. This is what we call the reattachment point. And then the flow will continue moving it, and then there will be a redevelopment of the flow. So these all are demonstrated in the figure, and the central region, that is the region away from the wall, will be a potential core zone. So this particular region, where region 2, 3, and I guess 4, these are very important for study of turbulence, because recirculation and separation and reattachment, these phenomena will give you a lot of good idea about the turbulent flow features. And from engineering point of view, we can say that the place where reattachment takes place, or the regions where there is a recirculation zone, there will be higher level of drag coefficient will be higher there, and skin friction factor, what we call. So these will be important. The calculation of the drag forces will be important from engineering point of view. From core fundamental physics point of view, we need to know the properties of turbulent flow in recirculation zones, or how turbulent flow separates, how we can do to either change the point of separation or reduce the recirculation area. So we need to study this. So that's why this simple looking problem is a good problem to study. It's easy as it seems easy, but it has a lot of very important implications. So now this was the style of content which you can find in textbooks. Like they explain everything, what is there, the phenomenon, what is the flow like. So now I will be focusing on one such paper which is there in the extensive literature which I showed in the previous slides. So they found out that there are some interesting experimental findings. So I'll begin with the first one. The double backward facing step. See, we saw there can be a flow in which only there is the expansion is only on the one side of the flow, and we can have in both the sides, like the pipe flow which I showed earlier. So in the double backward facing step or a pipe flow, although the domain is symmetric, we see that there are pipes which are symmetric domain, but the flow downstream of the expansion is found to be asymmetric. We find that the flow is asymmetric. How it can be asymmetric? That it was found that through experimental means originally, that after a particular expansion ratio of 1.5, by expansion ratio I mean the diameter of the larger tube divided by the diameter of the smaller tube. If that exceeds 1.5, then the flow is asymmetric. How asymmetric? See, basically the flow will definitely separate at the point of expansion, then it will reattach at some point. It was found that after the expansion ratio of greater than 1.5, that the point of reattachment or the reattachment zone, the length of that zone was different in the lower part of the tube and the upper part of the tube, making the flow asymmetric. That means that suppose the lower part of the tube has a reattachment length of 1 centimeter. I mean, reattachment length is the distance between the point of separation and the point of reattachment. And so suppose the reattachment, the length of reattachment zone is around 1 centimeter in the lower part of the tube, and it may be 1.5 centimeter, 2 centimeter in the upper part of the tube. So it was found that there is some asymmetricity in the flow. It was found that even if we take a 2D duct flow, somehow we make the conditions such that the flow should be two-dimensional, the input flow, the inflow, but after the expansion, the flow becomes three-dimensional. Anyhow, the expansion zone is such that the flow will have vortices, and the shear will develop such, the flow will be given such property that it becomes three-dimensional. And another important feature was that the flow at large distance downstream of the step gets redeveloped and becomes similar to the initial flow, similar to a fully developed pipe flow. Some after some particular distance after the reattachment. These distances are measured. They are very well experimentally measured and documented, and you can find in the literature, in the papers which I have given in the references. So, and a few more details which maybe a bit many people won't get through. So, stream-wise turbulent intensity. By turbulent intensity, there is for turbulent intensity, I can explain it as like I told about the mean flow and the fluctuations flow. So the mean flow will have three velocity components, u, v, and w. Similarly, the fluctuating flow will have three velocity components, small u, small v, and small w. So the turbulent intensity is u mean, the fluctuations, small u mean whole square. Similarly, small v mean whole square. So these streamwise, by streamwise turbulent intensity, I mean u. U is in the x direction and streamwise is x direction. So the streamwise turbulent intensity is found to be minimum at the center axis of the duct. The transverse turbulent intensity, by transverse I mean the small v along y axis. The transverse turbulent intensity has a flat profile in the core region and decreases rapidly at the edge of the recirculation zone. Going further downstream, the maxima coincides with the edge of the recirculation zone with the minimum intensities at the central axis. It means the nature has just reversed. Initially, it was decreasing towards the wall, and now it has increased in the recirculation zone, and it starts decreasing in the core region. So this is something interesting. The minimum TKE, by TKE I mean turbulent kinetic energy, which is just this turbulent kinetic energy is just the square of the fluctuating velocity components divided by 3. The mean u square, small u square plus small v square plus small z square, w square divided by 2 whole divided by 3. So the minimum turbulent kinetic energy downstream of the step at the center of the duct is approximately 1% of the kinetic energy of the mean flow. So as I already told that we have divided the turbulent flow into two parts, the mean flow and the fluctuating flow. So the mean flow will have kinetic energy corresponding to capital U square, capital V square, and capital W square. So we just do a comparisons between the mean flow and the fluctuating flow. If you do a detailed study about turbulence, or if you have taken a course on turbulence, you will read that, you will know that the turbulent flow or the fluctuating flow derive their energy from the mean flow itself through the mean shear, and then slowly the fluctuations start dissipating this energy into smaller and smaller and smaller eddies till they reach the Kolmogorov length scales, and at Kolmogorov length scales the energy is dissipated via viscosity. That's the Kolmogorov hypothesis of turbulent. We call this as the cascade theory, but this is not the topic. So let's again move back to the same topic. That so here we are doing a comparison between the TKE and the KE. By TKE we mean the kinetic energy due to the fluctuations. By KE it is the kinetic energy of the mean flow. So they say that the TKE is 1% of the mean flow, while the maximum TKE is at the edge of the recirculation zone. So as I already mentioned that the recirculation zone has higher turbulent activity, so there will be a higher TKE, turbulent kinetic energy. So now as we go further downstream, we'll see that the flow has fully recovered. These we have got the reattachment has taken place and the flow is now recovering and it is getting back to the fully developed flow. and it shows a profile of turbulence kinetic energy about 0.5% of the kinetic energy, the mean flow at the central axis, and increases to 1.3% at about one third y/L from the wall. So we also see that downstream of the step there is negligible shear stress at the center of the duct, and because I already told that it is a potential flow, there will be almost inviscid flow type of conditions will be prevailing. So there will be no shear stress because there is no viscosity. In the separated region, the shear stress increases to maximum at the edge of the recirculation zone. So as I already told that the recirculation zone will have higher turbulent activity, which is seen here. The peak of maximum shear stress decreases as the flow moves further downstream. It is decreasing. The peak means the maximum shear stress is decreasing because as we move downstream, the turbulent activity is subsiding because the recirculation zone is slowly vanishing. So we get the energy is dissipated and the shear stress is decreasing. The viscosity is decreasing. Look at some of the numerical studies of the problem, numerical treatment of the problem. So there have been many DNS studies have been conducted in the for the problem, and the DNS studies have given quite accurate results, uh, which have been validated by experiments. So I'm not going into too much details about the LES model, but LES studies have also been conducted, and there are some complicated issues arising in LES and DNS results. The important point is that DNS results have found very good very good agreement with the experimental results. That is what I want to convey as of now. There are some LEA studies which showed that there was some backward transfer of kinetic energy from the subgrid scale to grid scale turbulent motions, which cannot be described by simple eddy viscosity SGS models. So there are this in LES we just resolve the subgrid scales and then we try to find out the results. So it was found that the existing models which we used for LES, the eddy viscosity type models, they weren't giving good results. So it means that we need to improve the models. So means in general for a separated flow or for a reattaching flow, for a flow with recirculation, LES won't be giving good results. It means means LES will be giving results, but the eddy viscosity model with the simple models, they won't be giving results. So this flow, since it is simple to conduct experiments on this flow, we can get good experimental results, and then we can try to improve the LES models and then validate by the data of the experiments. So this studying this flow can help us develop better models for LES. So this is what I want to convey. So I conclude here. I think it was less of a paper type of thing, more of a literature survey or a review of the topic of the present research on this topic. So it was more of textbook type content itself, but it was something of a review paper type of thing. I will think so. I would like to conclude here that the turbulent flow through sudden expansion can give us very important and useful insights into the turbulent flow properties itself, as well as the engineering. There are a lot of industrial applications of the topic, so it can be helpful there. Moreover, there can be it can help us developing better numerical models for better CFD models for turbulent studies and for direct fluid mechanics itself. So I would stop here. Thank you for your attention. Thank you. So if anybody has some questions, either you can, if you're possible to unmute, or you can write in the. Okay, so Fine Mandal. Okay, let me answer these questions. Are all these flow zones obtained experimentally? Yeah, initially there were experiments. If you go through the papers which I mentioned there, I've tried to take papers from the 1970s, 1960s. So you see there, yeah, most of the flow zones were seen experimentally itself, and even I conducted experiments on the same the model which I showed in the introduction. There were, even I saw those flow zones. They were conducted experimentally, but there is one paper in Journal of Fluid Mechanics which has some analytical results which matches the flow zones, and they predicted it very well. But they have also validated their results, analytical results, using the experimental data which was conducted in 1960s, 1970s, and so on. So potential flow doesn't mean the velocity field can be described. Yeah, potential flow is by potential function is gradient gives the velocity. Exactly, yes. But that can be done. We can describe the velocity field by potential function only when the flow is inviscid incompressible and irrotational. Is the reason for asymmetric flow is gravity? No, there are. Gravity may be one of the reasons, but there are more complicated turbulence related things going on there. So there is but gravity can be a good reason. Yeah, I can send the PPT definitely. Yes, Kumar Shivam, you had one question. You can ask.
Okay.
Yeah.
Okay. So very beautiful presentation. Thank you very much. I was.
Your voice is flexible.
I am not a person from turbulent flow, or I don't study this topic, but I was interested. I was always interested in.
What are you from? What is your
Hello.
What is your background? You're from engineering?
Yes.
Hello.
I work in quantum information and mechanics. Hello.
Oh, great! Wow, that's great. Yeah, that's great.
So,
Great to hear
yeah,
from you.
thank you very much. Thank you very much, because I learned a lot, and I really learned something about the flow, and what are the questions, important questions people are asking, and how they are approaching it. Okay, thank you very much. But I had a very simple question. I wanted to just wondering, like, now here, how the study was done, that it was just expanded, right? The diameter of the tube was expanded.
Yes.
So now,
I didn't get the question. What do you want to ask exactly?
yes. So in what direction was the expansion? Was it the perpendicular to the flow, or was it the tangential to the flow? The expansion.
The expansion was perpendicular to the flow. Like basically, suppose you are having a pipe, and then you have another pipe of larger diameter, and you join them.
Okay.
Uh,
So it means that
Consider you have a pipe. Yeah, tell me.
Yeah. So that means there is a
Hello.
sharp difference in the diameter of the tube once the
Exactly. That's why the word is sudden expansion. There are flows where there is gradual expansion. There are studies conducted on gradually expanding flows, but here it is sudden expansion. There is a sudden jump in the diameter.
Okay. And one simple question, that when the motion becomes turbulent, does that mean that the velocity field cannot be described by a potential function?
Yeah, it's tough to describe a function, because when the flow becomes turbulent, there is a vorticity associated with. There are flow becomes rotational, so it will be tough to describe by potential function.
Yes. Okay. Thank you very much. Thank you.
Welcome. Thanks for attending. Regarding compressible flow to the same conditions, there is not much literature available right now, because for the compressible regime, even CFD models are not very much. Even means we don't have a lot of computational fluid dynamics models for compressible flow. Now combining compressible flow plus turbulence is like an amazing tough task. So as of now, not much work is available regarding compressible flow plus turbulence. It's tough to simulate compressible flow itself. The models are not validated right now, and then turbulence is also equally tough. Now combining both of them is a very big problem. It's a very tough task. So research is going on improving models for compressible flow, improving models for turbulent flows, and then combining them. It would be there. We can try doing that by studying FEM applications. I think FEM is generally singularity problem is limiting this kind of study when it comes to numerical analysis. No, there is not a problem of singularity problem in this case. It's there is like we have for turbulence, when you go for the Range decomposition, you will see that there will be in addition, after doing a Range decomposition, in addition to the Navier-Stokes equations, the four equations, Navier-Stokes and continuity, yet we need 6 more equations to find the eddy viscosity. So we need to find models for those equations. We have the K epsilon model, K omega model, SST models, and then we find it. So it's not exactly the singularity problem. FEM. Regarding FEM, generally for CFD, we use either FDM or FVM. FEM is generally not used for modern day CFDs, fluid dynamics. So I don't think FEM. Even I'm not much of. I don't know much about FEM because I'm working in fluid mechanics only. So FEM is. I don't think it's applicable in turbulence or in generally in fluid mechanics. What software? See, The softwares we can use, there are a lot of softwares. So the list is endless. But famous ones are ANSYS, COMSOL, OpenFOAM. There are open source codes available. You can write your own code itself. But the most famous ones are ANSYS, OpenFOAM, COMSOL, Converge, Star CCM, many others. OpenFOAM is a free software. It's open source. It's tough to learn initially, but since it's free, there is no license required. You can work anytime, anywhere. Concept of what can be use of this concept. So for applications, if you want, there can be a lot of engineering applications. Suppose turbulence is everywhere. It's almost everywhere. So it's there in the stars, it's there in the it's there in the designing a rocket. You need to study turbulence. Designing a aircraft wing, you need to study turbulence. Designing a simple pipe flow, you need to study turbulence. So it's atmospheric science. There is turbulence. If you want to predict the when cyclone will be coming, when anything, what will when rain will be coming, any climatic predictions or weather prediction, you need to study turbulence. So for application, suppose you have a aircraft wing. Now on aircraft, there is a point where separation takes place. So because of the flow separation, the lift of the wing decreases. So we want to increase the lift and decrease the drag. If we study the expansion, where the expansion geometry, we can know about the point of separation, the drag associated with it. So we can maybe modify the wing shape, wing profile, so that we can have better lift profile and reduce drag, so that performance increases, the fuel increases, efficiency increases. So then there can be a lot of applications. So generally, from engineering point of view, we study about pipe flows, duct flows on turbulent duct flows, turbulent pipe flows, and more about these airfoil flows in turbulence. But from core physics point of view, physicists study about homogeneous isotropic turbulence. It means turbulence without when in the core region. I talk about the core region. They study turbulence away from anyone. Like what is the exactly fluid nature of turbulence? What is the fluid behaving? What is what is causing turbulence? So they separate the one and they study there. So there is this research, and then there is turbulence in astrophysical flows. Turbulence is associated there also. So there can be a lot of research done from the core physics point of view. So I will share. I'll definitely share. So I hope, yeah, definitely clouds, atmosphere, turbulence. Turbulence is almost everywhere. There, I read many. It's like one of the biggest unsolved problems of physics. Turbulence is one of the biggest unsolved problems of physics. As for expansion of our PAE community, we were planning of these such meetings and some skill-based courses and projects. So this was the first general meeting. So we would expect that more of you would come up with you may read one single paper which may be simple, and we would like you to present the paper. Hopefully next week Surendra Padmata would be presenting few of his research work. If he's here, he can just tell you about that. But what we were planning was that more and more people can join this and they can present themselves. It would be a learning experience for all the listeners as well as the speaker, because you will learn to how to read a paper, how research is done, and then how to present it, and then even we can learn from your knowledge, and then we can just discuss questions. You may even I may not know many of the answers of, even if someone asks a few questions now, when I may not know knowing the answers. So that will be just a discussion kind of thing. You may know answer, you may not know an answer, but it's just increasing. So as part of the expansion of the community, we may be offering some projects. Any of you can experience offer a project. So basically, if anyone is from mechanical engineering background and interested in turbulent flows, then we can collaborate and do some small type of computational work related to this topic. So if anyone is interested, then you can contact me later for the closing of this first day of this journal club meeting. And I would expect more people to join in and share their research, share their knowledge and experience with us. Thank you all. Thank you for attending. Thank you for listening.